Chapter 2 is on atoms. So we said an atom was made up of protons, electrons, and neutrons. And the protons and the neutrons are in your nucleus. And we said the electrons are sort of in this cloud outside the nucleus. So our next section, we're going to get a little bit more specifically about where do we find electrons for specific elements. So we're going to start by defining some terms. So our first term is a shell, which is also called an energy level. So these two things mean the same thing, and you may hear me use those interchangeably. So shells are where you can find electrons. Within shells, we have what are classified as a subshell. And this is getting a little bit more specific of where can we find electrons in our atom. Within a subshell, we have an orbital. And again, that's getting even more specific where we're finding electrons for specific atoms. So let's talk about first the shell, or the energy level. And let's think about if I have this onion here, and I cut it in half and we see these rings. The center of my onion represents my nucleus. And then I have these rings around it. So the total amount of rings we could have in our onion, or our atom, here's my atom down here, are 7 energy levels. Within these energy levels is where we're going to find our electrons. And depending on how many electrons you have in your atom is going to depend on how big it is. So let's think about, like, if we have hydrogen. Hydrogen is atomic number 1, so it would have 1 electron. So hydrogen's first electron would go into energy level 1. So in our atom, this might represent hydrogen. So in the first energy level, that's where the electron can go. It's going to stay here. Hydrogen is going to be a small atom. If we have helium, helium has 2 electrons, these 2 electrons. So in the first energy level, we can hold 2 electrons. But as we get to elements that have more electrons, like lithium has 3 electrons, now where the next electrons are going to go is into the next energy level. So this first sphere around our nucleus is going to be called energy level 1. The second sphere is energy level 2. And we can keep going out to energy level 3, and then imagine I have more rings around here for 4, all the way up to 7. So there's 7 total energy levels, but depending on the element is going to depend on how many energy levels you're going to have. So lithium, let's go back to that. We have 2 electrons in the first energy level. The next electron would go into energy level 2. So there is a way we can calculate the maximum number of electrons in an energy level, and it's using this formula 2n squared. So if I'm in energy level 1, okay, that's my n, stands for energy level, I would have 2 times 1 squared. And 1 squared is 1, times 2 is 2. So the maximum number of electrons I can have in energy level 1 is 2, which is illustrated in the picture here. I can have less, I can have just 1 electron, but this is the max. If I was to go to energy level 2, so using my formula, n is 2, 2 squared is 4, 2 times 4, the maximum number of electrons I can have 8. So lithium had 2 electrons in energy level 1, 1 electron in energy level 2. But if the total amount, if I had a bigger element, we could see in energy level 2 we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. And as our elements get larger, we have more electrons, and you'll find as you go out to these higher energy levels, they can hold more electrons. So I may ask you, for example, what's the maximum amount of electrons I could have in, let's say, energy level n is equal to 4. Okay, so again, we just used our formula. 2 times 4 squared. Okay, 4 squared is 16. 2 times 16. The maximum amount of electrons in energy level 4 would be 32 electrons. Okay, so I'm going to give us an analogy to help us understand more about the terms shell, subshell, and orbitals. Okay, to help us understand the terms subshell and orbital, which are located within your shell, I have this apartment complex analogy. So looking at our key over here, An energy level, we also call that a shell, is going to be comparable. This is going to be at my apartment where I have these boxes on the left here. This is leading us up to, we're going to be creating something that's called an orbital box diagram, which is where you'll be putting electrons in these boxes to represent the electrons for specific elements. So we're going to do this pretending this is an apartment building, which is going to lead us into adding electrons for different elements. Okay, so in my apartment complex, I have floors. The floor is going to be comparable to my energy level or my shell. So this is floor number 1 or shell number 1 in my apartment complex. So it's a multi-story apartment. And in shell number 1 or floor number 1 of our apartment, the manager of the apartment lives there with his wife. And in floor number 1, we have a 1-bedroom apartment. So the box represents the bedrooms in our apartment, which is also going to represent orbitals when we're talking about atoms. So an arrow is going to represent the people. And the maximum people that are allowed per bedroom is 2 people. And if that's called an orbital for an atom, the maximum number of electrons per orbital that are allowed is also 2. So as I said, on the first floor, the manager lives here. So I'm going to represent the manager with an arrow. And again, the arrow really represents an electron. Electrons have a -1 charge. So we're allowed to have maximum 2 people per bedroom. This is one of the rules at the apartment. But they're both going to be represented with electrons. Electrons have a -1 charge, negative and negative repel. So when you draw these, you actually draw the arrows upside down, 1 up, 1 down. So in our apartment, the arrow represents the manager and his wife. They live in a 1-bedroom apartment on floor number 1. So that would be shell number 1 in our atom that can hold up to 2 electrons. So that might represent, for example, if I was doing an orbital box diagram for helium, helium has 2 electrons. So if we're looking at a pictorial view like our onion, you would draw maybe your 2 electrons in shell number 1, and an orbital box diagram you would represent like this. So there's 2 people living in a 1-bedroom apartment in floor number 1 or shell number 1 in our atom. And now when we come up to floor number 2, okay, that's going to represent shell 2 in our atom. We also have a 1-bedroom apartment available, and the maximum people allowed in a bedroom is 2. So we could draw 2 people in there. Okay, so this represents shell number 2. We could add, a couple more crosses here to represent electrons. But what you'll be doing is these box diagrams, not the sphere ones. I'm just doing that to kind of help show the image of what the atom actually looks like. And on floor number 2 of this apartment complex, we have a separate apartment available that has 3 bedrooms in it. So this is also on floor number 2. So we have 2 apartments available with a 3-bedroom apartment. Let's go ahead and give these addresses too. So the address tells us, again, the location of where somebody lives. If you want to go visit your friends, you need to know where to find them. Or it's also going to tell us the address of where you find electrons per specific atoms. So for helium that had 2 electrons, we would say that it's on shell number 1. So the way you would write the address is you go 1. If you have a 1-bedroom apartment, that's going to be indicated with the letter S. So its address would be 1S. If I go to floor number 2, the address here would be 2, and it's a 1-bedroom apartment. It's on floor 2. 1-bedroom apartment would be called 2S. If I want to go to the apartment with 3 bedrooms, it's still on floor 2. So I put it 2 because that tells me what shell I'm in. 3-bedroom apartments are called P's. Okay, so this would be called 2P. All right, so let's say we want to add some electrons to 2P. We said each bedroom can hold 2 people. Now, if we have 3 people that move into a 3-bedroom apartment, I have, for example, 2 sons in college, and when they go away to school and they're going to rent an apartment, They usually try to put the maximum amount of people allowed, and they're allowed, we just said 2 people per bedroom. But if only 3 people move in, are they all going to squish into one bedroom? No, you're paying more to have your own bedroom. So they're going to spread out. So if you have 3 bedrooms and you're adding electrons, you put 1 electron per bedroom or per orbital. Okay? And I also wanted to point out in my apartment complex, I have this E written on the side. The E stands for energy. Okay, so if we look at these bedrooms here, these are all equal in energy on my energy scale. The 2s apartment is lower in energy, the 1s is lower. The farther you go away from the nucleus, the higher the energy those electrons will have. So 2p, what I want to point out here is the p are equal in energy. So when you have a multi-bedroom, okay, like we just did here, we have a p, we call that a subshell. Okay, so the box is the orbital. In my p subshell, I have 3 orbitals. Now I can add more electrons here because we said we can have 2 electrons per orbital, or 2 people per bedroom. So if a 4th person moves in, we can add them in here. We can add another one and another one. So the maximum amount of people allowed into a 2p apartment is 6 people, or 6 electrons. So then we come up to energy level 3, or floor number 3 in our apartment. So we would call that address 3. It's a 1-bedroom apartment available here, so that would be 3S. Now we come up to another 3-bedroom apartment that's on floor number 3, or energy level 3. That would be 3P. So we could go ahead and add electrons in there, fill that up. The next one, as we're kind of seeing a pattern here, we go 1s, then 2s, 2p, 3s, 3p. Now we come to 4s. Okay, so 4s, we could put 2 electrons there. It's a 1-bedroom apartment. So anytime they're by themselves, that's an S if we were labeling our addresses where to find electrons. Now you notice here we have this 5-bedroom apartment. So again, these are all equal in energy. So that's going to be a subshell. So we have different kinds of subshells. We have a P, and now we have what's called a D. So if you have 5 bedrooms, that is a D. And the same rule is going to apply if you have 5 people that move into a 5-bedroom. They're each going to want their own room, so you would spread them across those equal energy orbitals. So that's one of the rules we're going to learn about when we start writing electron configurations. Now the thing that is interesting here, this is a D. It's actually 3D, not 4. So this is a part that's a little bit confusing, and I kind of like to think about houses that are split levels. It's not one complete floor. Like when I grew up, my house, I had a sunken living room, like houses built in the 70s. It's sort of a split level. And what was really happening in our atom is as you get farther from the nucleus, these shells get closer to each other. And as they get closer, there's a little bit of overlap. So the 3D, okay, is higher in energy than a 4S. So you might expect it to go 3S, 3P, 3D. But there's this little overlap here. So you're going to need to remember the order. And so the order we're going to be learning when you fill electrons into orbital box diagrams is the 1s, 2s, 2p, 3s, 3p, 4s, and 3d. So this is a little bit of an analogy to show you at an apartment complex to understand the terms subshell and orbital. And those again are located within an energy level, and they get more specific of where I'm going to find electrons for specific atoms. Okay, this is showing you what would look like an orbital box diagram that you could draw for a specific element, where you have, different amount of electrons in your atoms. So again, we have the energy level on the left. The energy is increasing up. So the energy levels that are furthest from the nucleus, so your nucleus would be down here, have higher energy. So electrons up in a 5s have higher energy than electrons in a 1s. So this would be the order. We would go 1s, 2s, 2p, 3s, 3p, 4s, 3d. And then the order continues on. As high as you need to remember is up to the 3d. We will stop here. If we had more electrons, if we had elements with more electrons, then we would continue on to 4p, then 5s, then 4d. And it continues up even higher into f's. Okay, so let's go over the terms again. So we have our shell as our energy level. Within our shell, we have a subshell. So again, a subshell contains orbitals that have the same energy level, and they're going to be the same letter to represent their location essentially. So in this shell, we're in shell number 2, or energy level 2. We have a 2s as one of our orbitals, and we have 3 2p's. And again, these 2p's are equal in energy orbitals. And when we have equal energy orbitals, just like we had a 3-bedroom apartment, we call that our subshell. Okay. Notice here that they're called px, py, and pz. That's being a little bit more specific than I'm expecting you guys to do. You'll just need to have the p's. But I'll show you what that represents in just a moment, the x, y, and z. The orbitals are where we're going to specifically find these electrons for different elements. The orbitals are actually electron clouds. These electrons are moving around constantly, forming these different shapes that we call clouds. Each orbital, as we said, can hold up to a max of 2 electrons. It can have 1 electron, but the max an orbital can have, again, our orbital was represented by that box when we did the previous diagrams. And then we gave an address of where do you find these electrons. So the orbitals are named, which is what we say our address, with the energy level, okay, where you'll find that electron anywhere between 1 and 7. And then we assigned S, P, and D. We can also do F. And we said that's based on the number of bedrooms or orbital boxes. What the letters really represent, so an S is when you have 1 box, the P was 3, but what it really represents is the shape that the electrons create when they're moving around. So an S represents a spherical shape. So this would be my S right here. And what that means is my nucleus is in the center. This is 3-dimensional, so it's an X, Y, Z axis. And the electrons are moving around outside the nucleus, and they're moving around very quickly, continuously moving, that they create the sphere shape. So the S really tells you the shape the electrons create. A P, okay, is when we have, again, we could have 3 p orbitals. The P represents the shape dumbbell. So that's illustrated at the bottom here. So again, we have an X, Y, Z axis. So this is showing you my dumbbell shape along the x-axis. And what that means is, again, the electrons are moving quickly. The nucleus would be the center. These are my electron clouds. Again, the electrons are constantly moving. They create the shape that looks like a dumbbell. So we have 1 orbital that would be on the x-axis. We can have another orbital of equal energy along the y and the z axis, the other 2 here. Okay, so that's why we have 3 equal energy orbitals, which when we drew our orbital box diagram, they could be px, py, and pz. What I want you to remember is there's 3 equal energy p's. The actual shape the p's make are the dumbbells. Now we also are learning d's. You don't have to know the shape for a d. After d would come f, which means you have a lot more electrons. You don't have to know this one. So you don't need to know the shapes for the d or the f. So here is showing us what would look like how the orbitals are named. So this would be the first one in energy level 1. And the S means there's 1 orbital that's in a spherical shape. Then we're in energy level 2. We have a spherical shape. In energy level 2, the P means we have the dumbbell shapes, and then etc. for the rest of those. Now we're going to go over the rules for writing electron configurations. The first rule says you're always going to put electrons in the lowest energy level first. This is known as the Aufbau principle. Okay, So as we said here, the electrons, depending on how many you have, you're always going to start at the lowest energy level, which is 1s. So if I had 2 electrons, they would go in here. If I have more electrons, I would start filling them up. And in our original example, we had boxes. You can draw these as lines and just imagine that's the bottom of the box. That just saves us a little bit of time instead of drawing a box around all of my electrons to represent that orbital. So the line is fine. So this is the order we need to remember. We have 1s, 2s, 2p, 3s, 3p, 4s, 3d. Okay, so we don't have to learn everything on this page represented in the diagram, but you do need to remember going up to 3d. So you need to remember this order of the lowest energy levels to the highest one of where you would put your electrons in. So this chart might help you remember the order of filling electrons into orbitals. You can either just memorize the order. As I said, we go 1s, 2s, 2p, 3s, 3p, 4s, 3d, and that's as far as we'll be going in this class. But if you were to take another chemistry class and you had to go up to higher orbitals, this chart would be helpful, and it may help you as well. So what we have here is the energy levels 1 through 7 on the left, and then we have the orbitals S, P, and D at the top header here. And then we're writing down 1s, 2s, 2p across, 3s, 3p, 3d, all the way across for each of my different energy levels or shells. But the way you fill the electrons is following this arrow down. It goes 1s, 2s, 2p, 3s, 3p, 4s, and that's where we end up with the 3d. So you can see where it seems like it's a little bit out of order. This chart may help you to remember. If you wanted to keep going, you could learn that, but for us, we're going up to 3d, and that's it. Rule number 2 is only 2 electrons per orbital. Again, that's the max. You can have less. And this is called the Pauli exclusion principle that tells us this. So let's look at an example. Let's start by using our elements. We're going to start with lithium. Lithium has 3 electrons based on our periodic table. You could look at the atomic number, which is your protons, which is equal to electrons. Now, to do the orbital box diagram, let's start with that. So how we did it in our apartment analogy is we had 1s, and then above that was 2s. Now, when you're writing them to save space, you can actually put these boxes, which represent your orbitals, right next to each other, just instead of taking up a whole page. But do remember that the 1s is lower in energy than a 2s. When they're right next to each other, it's not quite visible to see that. Okay, so we have 3 electrons. We're allowed to put 2 electrons per orbital, and the electrons are represented by our arrows. And you put them in opposite spins because, again, as I said, they're both negative. So you put 1 electron here, then the next electron next to it, but upside down. Then you go to your next energy level. So I can do this one up here as well, 1, 2. And I have 1 more electron that's going to go into energy level 2 in my S. Okay, so that would be my orbital box diagram for lithium, which is like our apartment analogy we did. Now, the electron configuration is a shortcut way. Instead of drawing out these boxes like this, the other way you could do this without doing the boxes, you could go 1s with a line, 2s with a line. And again, the line represents the bottom of the box, and you can do an arrow up, arrow down, and another arrow. So this would be acceptable for you guys to report when you're doing orbital box diagrams. So let's go to our electron configuration. This is a shorthand way to show the same thing. So we write 1s to show, again, my location of where the electrons are. The superscript at the top tells me the number of electrons that are in that orbital. So in my 1s, I have 2 electrons, so I have a superscript 2. In my 2s, I have 1 electron. So I must show that. You can't, if you have 1, you can't just leave it empty. You have to write that superscript of 1. So at the bottom here, again, my orbital box diagram, the box represents the orbital and the arrows are the electrons, and you draw them in opposite spins. So that's an orbital box diagram and an electron configuration. So again, an electron configuration tells us where the electrons are located for specific elements. And as we just showed how to do on the previous slide, if I had hydrogen, hydrogen has one electron because its atomic number is 1, which means we have one proton. So to do the electron configuration, we say it's an energy level 1. So its box diagram would look like this, 1s with just one arrow in it. To do its electron configuration, I write 1 to show me the energy level or shell. S tells me the shape it's going to create is a sphere. And the 1 superscript is the number of electrons in that specific orbital. The next rule for writing electron configurations, number 3, says don't pair electrons until you have to. This is called Hund's rule. And if we look at, for example, we have nitrogen. Nitrogen, if we look at our periodic table, has 7 protons, therefore it has 7 electrons. So again, we need to remember our order. We put the first 2 electrons in energy level 1, then we're jumping up to energy level 2. 2s is lower than 2p, so we can put 2 in there. And now we've used up 4 electrons, we have 3 left. Now we're at the equal energy orbitals, 2px, 2py, and 2pz. And what we said earlier is the department manager only lets a maximum of 2 electrons per orbital. And if you have a 3-bedroom, your tendency is you're going to want to spread out, 1 person per bedroom. Well, if you're an electron going into an orbital, again, electrons have that negative charge. They're going to repel each other. So if we have equal energy orbitals, those electrons are going to spread out. So that's what Hund's rule says. You're not going to pair them up unless you have to. So you're always going to spread them out first. So we've used all 7 electrons. This would be my orbital box diagram for nitrogen. Now the electron configuration, again, is the shorthand method to show this. So in energy level 1, we have 1s, superscript of 2 to represent 2 electrons. We have 2s, lower in energy with 2 electrons, so we have a superscript 2. And then in our 2p's, we combine them all together. We don't do 2px, 2py, 2pz. We say the total amount of electrons in all of our p's is 3. So when you write the electron configuration in the shorthand method here, it doesn't really show me if you know Hund's rule. So you will be asked to do orbital diagrams because that shows me if you know Hund's rule, those electrons need to be spread out. And then you would pair them if we have more electrons in a higher element. Write electron configurations for the following elements. So we're going to start with Na, which is sodium. First is to figure out the number of electrons. So we need to use our periodic table, and we can find sodium here has 11 extra electrons. So we're going to do the orbital box diagram. And again, we can start by just drawing a line to represent the bottom of the box. We always start with 1s, and we put in 2 electrons. Then we go to 2s, which can hold 2 electrons. Then 2p has 3 orbitals. So we can go ahead and spread those out first, and we need more electrons. Now we pair them up. So we've used a total of 10 electrons so far. We have 11, so we need to keep going. After 2p comes 3s. So we put 1 electron in 3s. Now the electron configuration is the shorthand of the orbital box diagram, so we can write that out. 1s squared, 2s squared, 2p, total electrons in 2p is 6, and then 3s, 1. That's my electron configuration for sodium. Now we go, potassium is right below, so that one has 19 electrons. So we're going to follow our order again. 1s with 2 electrons, 2s with 2 electrons, then we have our 3 2p's. Spread them out first and then pair them up. We're at 10 electrons, then comes 3s, which can contain 2 electrons. Then we go to 3p. And again, we spread them out first, then we pair them up. And right now we've used up 18 electrons. We have 19. After 3p comes 4s, and we put 1 electron there. So now the electron configuration goes 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s1. And if you do enough of these electron configurations, you are going to quickly have that order memorized. Now, iron in our periodic table is one of our transition metals. It's in the center there. It has 26 electrons. Fe is iron. So same thing, we're going to go through and do our order. I'm going to try to write down here so I have more space. 1s with 2 electrons, 2s, 2p, which has 6 electrons. Then comes 3s. Then we have 3p. With 6 electrons, 4s with 2 electrons, we're at 20. And then after 4s, we have the d's. And in the d's, we have 5 equal energy orbitals, and that's the 3d. Okay, so 4s to 3d. And now the d's are just like the p's. We have equal energy orbitals. So based on Hund's rules, we're going to spread them out as much as we can before we pair them up. So we have 6 electrons left to go. So I spread out the first 5. Okay, based on Hund's rules, they're spread out. And then I add 1 more arrow in the opposite direction. So that would represent iron with 26 electrons. So its electron configuration, all right, right above it is 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s squared, and 3d6. Now, as far as writing electron configurations go and orbital box diagrams, you need to be able to do them up to atomic number 30, which basically would take us up to filling the 3Ds, because iron had 26. If we had 30 electrons, we would fill in those 4 electrons that are unpaired, and we would pair them up. And that would basically take us up to atomic number 30 is Zn. So be able to write electron configurations for all the elements up to atomic number 30 or zinc. Another way we can write electron configurations is what we call a noble gas shorthand electron configuration. So as a reminder, our noble gases are the family of elements at the very end of our periodic table. It's either in this periodic table column number 18, or some of them are labeled as main group number 8A. So this is where we find our noble gases. So to write a noble gas shorthand electron configuration, what you're going to do is you're going to find your element sodium. Okay, it has 11 electrons. You're going to find the noble gas that has the amount of electrons closest to sodium but not more. So in this case, it's going to be neon. Neon has 10 electrons. So we did the electron configuration for sodium previously, which we have displayed here. Now neon has 10 electrons. So what we can say is the first 10 electrons from sodium, which has 11 electrons, would represent neon. So how you write a noble gas electron configuration is you put the noble gas in brackets. So neon, that represents 10 electrons. Sodium has 11, so then I have to write 3s1. That would be my noble gas electron configuration for sodium. Potassium is right below sodium. Okay, so potassium has 19 electrons. So you find the noble gas that has the closest amount of electrons, but not more, is argon. So argon has 18 electrons. Okay, this is 18 electrons, which would represent argon. So you would write argon with brackets around it, and then include the 4s1. So that would give me 19 electrons. Now the next one we have is iron. Iron, we said, had 26 electrons. So we look at iron in our middle, right here. And for iron, the noble gas would also be argon. Argon would again represent these 18 electrons. So I could write argon with brackets, and then what's left is 4s squared 3d6. So 18 electrons plus the 2 would give me 20, plus 6 more in the 3ds would give me 26 electrons. So these are how to do noble gas shorthand electron configurations. We can use our periodic table to do noble gas electron configurations. So in the previous example, you had to write out the whole electron configuration to figure out the noble gas electron configuration, which is supposed to be a shortcut. So we're going to learn how to use the periodic table. So a couple of things let's point out on our periodic table first is we have our periods again, which are our rows labeled down here 1 through 7. Across the top we have our groups. So we have group 1, group 2, and then it's going across up to group 18. Sometimes we look at our main groups, and this would be group 3, 4, 5, 6, 7, 8. Either way, your periodic table might be labeled. Now, what I want you to notice is if we're looking at group 1, the electrons that are coming here are going to be the last electrons going in. They all end with an S and a superscript 1. That's where their last electron is going in. The difference is the number in front, which is the period. So it's 1s1, 2s1, 3s1, etc. The second group, group number 2 here, they end in S2. All of them are the same. The only difference again is the period they're in. And then if we jump over to group number 3, we notice here that I'm in period 2 and it ends with an S2 and a P1. And then we jump down one, same thing, we see S2, P1. So you can see there's trends in our periodic table. And again, this explains why these elements behave similarly. If we were to go to group number 4, notice that the number of electrons going in here, the last ones are S2 and P2, and then etc. going across. So how can we use this to help us do an electron configuration? Let's do an example of an element with a higher amount of electrons. Then I'm going to be asking you to do the complete electron configuration. But for doing a noble gas electron configuration, you can do some higher ones. So in this example, I have barium with 56 electrons. Okay, noble gas electron configuration is we find the noble gas with the closest amount of electrons that's smaller. So in this case, we would have xenon with 54. So noble gas electron configuration, we would write xenon. In brackets, that represents our first 54 electrons. We have to have 56, so we have 2 more electrons. So what we do is we can look at the period. It's in period 6. And then we know that everything in group 2 is going into an S2. So that would be my noble gas electron configuration for barium using our periodic table. So if you notice on the periodic table here, it's also color-coded. Everything in blue here are the S's. Everything in pink are where we're putting electrons into the P's. And then the yellows, there's our transition metals, we have electrons going into the D's. The greens down here we don't have to know, but that's where electrons would be going into the F's. So this periodic table is again highlighting where you find your S block in purple here, your P block in green, and then in red your D block. And we're not going to worry about F's. So this is also showing you the order that you're filling your electrons. So notice we do 1s across the top. This S here is an exception because that's where you would find helium, that you could put 2 electrons. So that's still in your 1s. And then you go 2s across to 2p, 3s to 3p, 4s, and this is where we take the drop down to 3d. So that's where I said you kind of have that overlap in orbitals as you get farther away from the nucleus. So this shows you the order of how you would put electrons into your electron configuration. So let's use the periodic table to do a noble gas electron configuration. What is the noble gas electron configuration for calcium? So we find calcium here. It's element number 20. Noble gas electron configuration is we look at what element is our noble gas, is argon, that's closest to it. So argon represents our 18 electrons. Calcium has a total of 20. So we're going to count what period it's in. So we go down 1, 2, 3, 4. And then the second column is S2. So it's argon 4s2, and this would represent our 2 electrons for a total of 20 electrons. Valence electrons are your electrons that are in the outermost shell of your atom. So they're going to be the ones that have the highest energy level or shell number. So for example, if I do an electron configuration for phosphorus, I have 1s2, 2s2, 2p6, 3s2, 3p3. My highest energy level is the one with the biggest number, so that's energy level 3. The number of valence electrons would be if I added these numbers together. So 2 plus 3 would give me 5 valence electrons. And if I wanted to draw a picture of my atom here, they're the ones in the outermost shell. So let's count. This is the P represents my nucleus in the center. This is shell 1, shell 2, shell 3. In shell 3, I have 1, 2, 3, 4, 5 electrons. So that's a term to remember. Valence or electrons are the ones in the outermost shell. Core electrons are going to be the electrons total in all of those inner shells. Okay, so our core electrons here are in shell 1 and shell 2 combined together. So we have 2 in the 1s, we have 2 in the 2s, plus 6 in the other 2p. That gives us a total of 10 electrons for our core electrons. So sometimes I think of core being the center, like the core of the Earth is the center of the Earth. Or maybe if I'm working out my abs, I'm going to do my core workout. Your abs are the center of your body. So you can think about in an atom as well. Your core electrons are all the ones in the center here. Okay, so there's a total of 10 electrons there. Those are all my core electrons. Valence means outer shell electrons. Lewis dot structures are a way to show valence electrons for specific elements. And how we do that is you write the element symbol, and your element symbol is going to represent the nucleus and all the core electrons. So let's go back and look at our atom of phosphorus again. So again, the green circle in the middle represents our nucleus. The core electrons are shell 1 and shell 2. The valence electrons would be in shell 3. So you're going to write the element symbol, P, to represent the nucleus and the core electrons. And then the valence electrons for phosphorus, we have a total of 1, 2, 3, 4, 5. Go ahead and circle our valence so we can see. We have 5 valence electrons. So how you write the Lewis dot structure is you write the valence electrons as dots. And you're going to surround your element symbol with your dots. And you draw 2 dots per side. That's a maximum. You're going to have 1 dot on the side. The maximum amount of total electrons you could have for valence electrons is 8. So phosphorus has 5, so you just write element symbol P, and then you draw your 5 dots around them. So you could do 4 first and then pair up the last one. Your group number corresponds to your number of valence electrons for your main group elements. We're not going to worry about transition elements. There is an exception for helium. So helium's not going to match. So for example, if we look at group number 1 on our periodic table, all the elements in group number 1 have 1 valence electron. As we saw earlier when we were doing the electron configurations, those would all be S1. That's the outer shell or the last electron that's going in. So to do a Lewis dot structure, you just have to write the element symbol. So for example, if I have lithium, I draw lithium and then I put 1 dot because it's in group 1. If I have Beryllium on my periodic table, it's in family 2. So it will have 2 dots. So the element symbol and 2 dots, etc. I could go all the way across. Let's say, for example, if I wanted to do krypton. Krypton is in column 8. So I would just write Kr for krypton, and then I would draw my dots around it. And I have a total of 8, and now I'm going to pair them up. So I have a max of 2 on each side. That would be my Lewis dot structure for krypton. So the periodic table is very useful for doing Lewis dot structures. You just have to know what column your element is and use that as your valence electrons. So this periodic table again has the electron configurations for the valence electrons for the different elements. So again, in group number 1, we see that they all have 1 valence electron in the s. In group number 2, they have 2 valence electrons. When we come over here to group number 3, there's 2 electrons in the s and 1 in the p, so our total amounts in the p here is 3 valence electrons. Column 4, we have 2 in the s's, 2 in the p's. That gives us 4 valence electrons. If we go to column 5, we've got 2 in the s, 3 in the p. We've got 5 valence electrons. As we go all the way across, we'll look at column 8. Again, we have helium as an exception because it's in shell number 1. It can only hold 2 electrons. But if we go down to neon, we have 2 in the s and we have 6 in the p. So we have 8 valence electrons for everything in column 8. Write the Lewis dot structure for silicon. So we find silicon on our periodic table, and I'm circling it, and we look at what column it's in. And again, this applies for our main group elements. So I'm going to label these 1, 2, 3, 4, 5, 6, 7, 8. And it's in column 4, so it's going to have 4 valence electrons. So we have silicon, and then we just surround it with 4 dots, and that's my Lewis dot structure for silicon. How many valence and core electrons does bismuth have? Bismuth's symbol is Bi, so we find Bi on our periodic table. It's atomic number 83, so we know the total electrons is equal to 83. Now, we could do the whole electron configuration, but I told you only had to know up to 30, not 83. But we can use our periodic table to help us find out how many valence and core it has. So valence electrons are equal to your group number. So our group that we're in, again, this is main group, so we can't see 1 and 2, but this would be groups 3, 4, 5, 6, 7, 8. The group number is your valence electrons. So the valence electrons for Bi is 5. Now our total electrons is 83. Core electrons is everything in all those inner shells. So it's just going to be 83 minus 5, which would give us 78 core electrons.